So now we'll be discussing Kirchhoff's voltage law, and just like how the current law was the first law, this is also called the second Kirchhoff's law. So what does this really state is that the sum of voltage drops so voltage drops across components like resistors, diodes for example, is equal to sum of voltage gains. So voltage gains are across power sources like batteries for a closed loop. And similarly, similar to the Kirchhoff's current law, there's an alternative statement here as well, that instead of saying sum of voltage drops equals sum of voltage gains, you can also say that the algebraic sum of the voltage or the potential difference in a closed loop is 0. So you have both of these statements that you can write in an exam when they are asked. But now we'll be having a look at some of the examples to get a further grip of this concept. So let's have a look at this one then. So the circuit diagram below is for the rear windscreen heater of a car. It consists of 4 heating elements, each of resistance 6 ohms connected to a 12-volt battery of internal resistance 2 ohms as well. So in your paper you will have something like this drawn. So just to underline the idea of internal resistance a bit more, you will have a dotted region here to show that this is part of the cell and this 2 ohms is the internal resistance. In the first part we have to calculate the current and also the potential difference across each heating element. So on first sight this circuit may seem a bit tricky to solve, but the fact that all of these heating elements, the resistors, have equal resistances does simplify things by quite a lot. So first we can combine both of these. So remember that whenever you have identical resistors in parallel, the effective resistance is the resistance of one divided by the number of resistors in parallel. So if you have two 6 ohm resistors in parallel, the resistance would be 6 upon 2, so it basically becomes half of its value. And then similarly for this one as well. So you have a 2 ohm resistor, another 3 and another 3 ohm resistor which are in series. So then you can calculate the current, So in A part 1, the current I would be V upon R. So V is 12, and the series current which is going to be flowing throughout this major part, not through the branches. We will talk about the branches later. So that would be 12 upon the total resistance. That would be 2 plus 3 plus 3. So 12 upon 8, which is 1.5 amperes. Again, alternatively, some of you might think that we can also use the voltage approach for the potential differences. But remember not to make the mistake of saying that 6 volts appears across this and 6 volts appears across this, because we just found out that both of these have equal resistances. It's not going to be that case because you also have the internal resistance here, and the technical term is that there would be some lost volts across this. So remember not to make this mistake. So we know that the current flowing is 1.5 amperes like this, and then when it faces two equal resistances, it would split up into two equal parts as well. So it would split into 0.75 and 0.75, half of 1.5. Then it combines back up again to become 1.5, and then again it splits into 0.75 and 0.75. So the current across each heating element is going to be half of 1.5 is going to be 0.75 amperes. Now in the next part, because we have we did a lot of analysis in thinking outer approach to the first one, so the next part is not going to be as difficult, because all the resistors are 6 ohms, all of these have this current flowing through them. Then we can just use V equals to IR to find the potential difference across each. So 0.75 times 6, which is going to be 4 volts, right? So once this is done, part part 1, calculate the power dissipated in each heating element. So B part 1, power in each heating element. We have all the formulas. We can actually use any one that we want. We can use VI or I square R or V square upon R, because we have found everything related to the heating elements. We can use any of those. Let's just go ahead and use the simplest one to work with, VI. So the voltage across each of those is 4.5 and the current through them is 0.75. So then the power would turn out to be 3.375 exactly, so 3.4 watts to 2SF. And part 2 says in the battery due to its internal resistance. So for this one we would have to use I square R. So the current flowing through this is also going to be the same. Sorry, so 0.75 was the one flowing in the branches. So the one flowing through the 2 ohms would be this 1.5, which was the current throughout this major part of the circuit. So 1.5 squared times 2, right? So this turns out to be 4.5 watts. And again, if you remember the videos in which we did the KCL examples, you would remember that what we found out was that in each case the power supplied by the battery would be equal to the power dissipated across the different components. So if you also find this as the power across one heating element, so times 4 plus this power, which is across the 2 ohm resistor, must equal the power supplied by the battery. So that would be this voltage multiplied by this current flowing through the cell. On to the last part, which asks, how would the operation of the heater differ if the heating elements were in parallel with each other with the battery connected across the parallel combination? So if we had this source and this is again part of the cell, so in parallel with this you have the 6 and the 6 and the 6 and then the fourth 6. So how would the operation differ? So again, if you think about this in terms of the formula, so we know that the formula that we use for power are 3, and now we need to decide on which one are we going to talk about when we need to analyze what is going to happen to the power. So we can also go with current, but current is going to be a bit more difficult to analyze and it would need some calculation, because you might be thinking that if all of these are in parallel, then the total current would fall. The total current would rise because the total resistance would fall, and this is correct, but then that current would also split into each of the branches, right? So then we don't know what exactly would happen. So let's try to talk about the other formula, the one which involves voltage and current, right? So what would happen to the voltage, because the resistance is going to stay the same, and then what happens to the voltage is also what would be happening to the power. So in this case, the voltage across each heating element was 4.5 volts, right? So if we also calculated the power for each heating element using V square upon R, so that would be 4.5 square upon this 6, whatever that answer was. Now if we do the same thing for the parallel combination, then the voltage across each of these 6 ohms resistors are now going to be 6 volts, right? So the power goes up because the voltage has gone up. So now more power would be dissipated across each of the heaters. So now this means that more power would be dissipated. And this is good for a heating application, because that means that more electrical power is dissipated as heat. Now this question, for the circuit in figure 10.15, the EMF of cell 1 is 6 volts and cell 2 has an EMF E2, right? So we do not know what this EMF is. Resistance values of the resistors R1 and R2 are 5 ohms and 3 ohms respectively. Current in the circuit is given. Calculate the EMF of cell 2. So what we then see is that there is also some current marked I. Now the idea is, and some of you might immediately notice that this is the positive end of cell 1, negative of cell 2, and then this is connected basically in opposite. We know that the ways that we connect the batteries are the positive of a battery is connected with the negative of one if we want the voltages to add up, right? But let's scratch that thought for now and let's try to think according to KVL. So we know that we have these two cells. We can see that cell 1 we know the EMF for, and if we think about this, how is it trying to drive the current? Then it is trying to drive it from the positive to the negative terminal, which is also how I is labeled. And then cell 2 is trying to actually drive it in the opposite direction from its positive to its negative terminal, right? So we need to find E2. So let's do this, that because E1, the EMF source of cell 1, we are going to take as positive because that's exactly how I1 is flowing. But E2 we are going to take it as negative because E2 says that the current should flow like this, whereas actually it's marked like this. Even if this one was not labeled, I would have to take this decision of taking some current, right, either this or this, and then marking one of the EMF, one of these cells as positive, the other as negative. So when we write the statement for KVL, so the sum of potential gains should be equal to the sum of potential drops So I know that for this one, because we have two cells, so we know this is what is going to make the potential difference go up. So for the first cell, I'm going to take this as positive because this is how the current is flowing, positive to negative. Some of the people also like to think of it like this, that if the current is leaving the positive end of the battery and going into the negative, I'll take that cell as a positive. But for cell 2, the opposite is happening. It's actually entering into the positive, which is wrong. It must be flowing the other way around. So I'll take this cell as negative. That must be equal to IR1 plus IR2. So the potential drops across both of these, right? So it should be equal to IR1 plus IR2, or you can also write it like this. This is something that you'll also see with the math, that you can factor out the I, or you can also use the physics behind this, that resistors in series get added. So we need to find the EMF of cell 2. So E1 was given as 6, E2 is what we need to find, I is given as 0.5, R1 is 5, R2 is 3. So 6 minus E2, so equals 0.5 times 8, which is 4. So E2 equals 2 volts, right? So this is the EMF of cell 2.